Thank you for the opportunity to speak at JuliaCon. My name is Erich Focht. I work for NEC, and this work has been done together with Valentin Churavy from MIT. The title of the talk is Julia on the SX-Aurora Vector Engine. What is a vector engine? The vector engine has evolved from a long series of vector supercomputers that NEC has developed since decades. The first one marketed commercially was the SX2 in 1983, and it was the first computer with a performance larger than 1 gigaflop, and the first computer featuring multi-lane pipelines and vector caches. These computers were mainframe-sized, and they were designed for high sustained performance. I'd like to remind you that back then, 4 decades, the vector supercomputers were the general-purpose machines for doing high-performance computing. The high sustained performance of these machines is reflected in their bytes per flop ratio. So we started with 8 bytes per flop. You see that number is shrinking over time. The reason for this is that silicon structures have been shrinking, and it was possible to add more and more compute units to the processors, but the memory bandwidth could not keep up with this development. Still 1 byte per flop, the last machine, the SX-Ace, released in 2013, had 1 byte per flop, is not a bad number, and that is reflected in the fact that this machine had the best HPCG efficiency with 11%. HPCG is one of the 2 important benchmarks for high-performance computing, besides the LINPACK, which measures basically the peak performance of a computer. HPCG measures more of an application performance. It is a conjugate gradient solver with multi-grid preconditioning. Now, these big machines are now shrinked to the size of a PCI Express card, and this is what we call the Vector Engine card. The Vector Engine card comes in 3 flavors. One for passive air cooling for servers, another one for active cooling for workstations, and the card for bigger installations with direct liquid cooling. These cards are built into servers, normal Linux servers. The biggest server features 8 of these vector engines, and these servers are assembled to clusters. We have many installations. Some bigger ones are on this list, on this slide. You see here Deutscher Wetterdienst is the weather service for Germany, has 2 large installations, a total of over 6,000 vector engines. Jamstack, the Earth simulator in Japan, has 5,400 vector engines. There's National Institute for Fusion Science, 4,300 vector engines. These are large systems. Then there are some smaller installations, another climate site in Czechia, and various academic sites. The Vector Engine processor has meanwhile reached version 2.0, is built in 16 nanometer technology. So this is a technology of the year 2017, 2018. You see here a picture of the chip. The chip is built with HBM2 memory stacks, 6 stacks on a substrate, and the chip has only 8 or 10 cores. That means we have very few cores, but the cores are very strong. So the core performance is 307 gigaflop in double precision, 614 gigaflop single precision. The cores are arranged on a 2D network on chip, and they are connected to a last level cache, 16 megabytes, which is then connected to the HBM2 memory. The total memory bandwidth of this chip is 1.53 terabytes per second. As a PCI card, the TDP of it is 300 watts. We see 200 watts for normal applications or less. Total memory capacity of this chip is 48 gigabytes. Something that I'd like to explain before continuing is what's the difference between SIMD and a long vector system. So SIMD is depicted on the left. You see this is a sketch of a vector operation, vector A plus vector B equals vector C. And when the instruction is issued, the content of the vector registers or SIMD registers A and B are loaded into the SIMD pipeline, in the add pipeline, and processed for a certain number of cycles until the result is delivered to the result SIMD register. That example could be taken from AVX2 processor. This is the way an AVX2 processor SIMD unit actually looks like and operates like. A vector register, a long vector register, looks differently. It has a certain SIMD width, but the register has also a depth in cycles. So for the vector engine, the SIMD width is 32 times 64 bits, so 2048 bits, somewhat similar to what an SM in a GPU, in a NVIDIA GPU is. And the depth of 8 cycles leads to a vector register size of 16,384 bits. So actually we have 16,384 bits, but they are processed not in one cycle, instead they are processed in 8 cycles. The impact of this is that one instruction issue triggers work in the vector add unit for at least 8 cycles. That means an instruction issue is triggering a lot of operations, actually 256 operations. And therefore the ratio between usefully spent time and idle time of this unit is higher than of a SIMD unit. So it is harder to actually keep a SIMD unit busy than a vector unit. Why? Because parallelism is expressed in the instruction set architecture and is a lot wider. Now, the vector engine card in a different view is here. You see it's a simple PCI Express card, basically containing a lot of voltage regulators and a bit of electronics and the chip. We have accumulated since 2017-2018 a set of SKUs of this processor with various memory bandwidths and frequencies and performances. This card has high sustained performance. The byte per flop ratio of it is 0.62. Thus, it's still a very good balanced processor. I'd like to remind you that for normal CPUs and GPUs, this byte per flop ratio is in the range of maybe 0.1 or sometimes even less. So this leads to a high performance HPCG performance efficiency of 6%, which is a very good number. Marketing wise, I'd say there is this card reduces the total cost of ownership, because basically due to the long vectors we achieve lower power consumption than normal processors, and we have pretty good productivity in programming because this processor is being programmed with normal programming languages. So it is rather easy to program and easy to maintain the code. Here's a list extracted from last year's top 500 rankings for HPCG, the sparse matrix inversion benchmark, which is sensitive to memory bandwidth, and HPL, high performance LinPack, which inverts a huge dense matrix. As you can see, in HPL, the Earth simulator and the plasma simulator are ranked on the places 39 and 54, while in HPCG they show up pretty close to the top. This is due to their high memory bandwidth and good execution efficiency for HPCG. Another benchmark example from meteorology shows that using a certain amount of power, a limited amount of power, will give you a factor of 2 to 7 in performance with SX-Aurora Tsubasa compared to Epic Rome nodes. In seismic imaging, the situation is quite similar. Here we compare two benchmarks, one executed on a dual socket Skylake cluster, one on 1 Volta 100 V100 card, and one on a vector engine. Somewhat to the system software. The main execution mode of the vector engine is the so-called VE native mode. In that mode, an application is loaded entirely onto the vector engine and run from the vector engine. The application can execute system calls. The system calls are handled by the operating system of the vector engine, which is called VEOS, and runs mostly in user space on the Linux server. This way the application actually feels as if it would be running natively on a vector engine processor, which is a little special, but being able to execute system calls under Linux, it feels as if it's running under Linux on this vector engine, although it is not. So in this execution mode, the vector engine operating system is offloading the system calls of the application. Then we have accelerator mode execution with APIs called VO or VEDA, and reverse offloading. So in VO and VEDA, the main program runs on the vector host, and this main program can offload execution kernels to the vector engine. It's a similar usage mode like OpenCL or CUDA. And in reverse offload mode, we actually run the vector engine application, the main program of it, on the vector engine, but can offload kernels to the host. Programming the VE is usually done in C, C++, or Fortran. These are proprietary NEC compilers which are able to auto-vectorize and auto-parallelize programs. Parallelization inside one vector engine can be done with OpenMP, or it can be done with MPI. MPI can also be used, of course, to parallelize across larger clusters over InfiniBand with peer direct VE to VE transfers. There is also a hybrid MPI, a truly hybrid MPI that supports MPI between processes running on the vector engine natively and on the vector host. We have started an effort to port LLVM for the vector engine. This version of LLVM is open source, and it supports OpenMP target offloading from VE to VH and from VH to VE. LLVM is actually the glue to the Julia language. There are two LLVM implementations for the SX-Aurora, two efforts. One is the open source one, started in 2018. This was started as an alternative compiler for SX-Aurora. It was experimental. We upstreamed a lot, and since December 2021, this is among the official architectures. Finally, getting to the VectorEngine.jl Julia module. This is work in progress. The main Julia code runs on the host CPU, currently on an x86-64. And by loading VectorEngine.jl, you are attaching a vector engine core to the Julia program. It enables offloading Julia functions currently with similar limitations like for GPUs. Vector engine code is just-in-time cross-compiled for the vector engine by calling LLVM-VE APIs directly inside Julia. Vector engine code is loaded into the device and executed as needed. As some of you know, integrating support for vector engine means deep integration with LLVM-VE, VE-specific offloading methods, and finding specific solutions for supporting VE's peculiarities. The simplest way to integrate the vector engine was to use GPUCompiler.jl, which is the basis also for CUDA.jl, AMD GPU.jl, and OneAPI.jl. It compiles accelerator device kernels, which are functions with certain restrictions. Also, you need to take care about the arguments that you're passing to these kernels, as not all data types or structs are available on the device side. Compared to native or host Julia, there is only a very basic runtime on the accelerator side. This limits a lot Julia features that can be used on accelerator side. Offloading is done with VEDA. VEDA is the Vector Engine Device API, very similar to the CUDA Device API. VEDA is built on top of Avio, the Vector Engine offload libraries. The logic of this is hidden in the Julia module VEDA.jl, and we're using the VEDA library through auto-generated APIs using CCall. Unlike GPUs, we are able to pass arguments on the call stack of kernel functions, and this avoids additional transfers for passing smaller objects or structs to the accelerator kernel. Device memory management is done with a structure called device buffer. This is a structure that contains information needed on host side to manage device memory. It allocates asynchronously the memory on the device, but for now we have to resolve the virtual pointer that is returned by VEDA to a real vector engine virtual memory address synchronously. When the device buffer object is deleted on host side, the device memory is freed asynchronously. Here's a simple hello world example for kernel execution. First load the module, then define the kernel. In the kernel, of course, we need to take care that we don't use any of the non-existing Julia runtime functions. So this is why we call VEPrintf the VEPrintf macro instead of something else. Finally, we compile the kernel and launch the kernel. And at the end, we call synchronize to make sure that everything has finished on the device. A simpler way to express this in a line is by using the VEDA macro, which is very similar to the macros CUDA, ROC, and VEDA API. While calling kernels is very similar to what's being done on GPUs, when passing arguments, we have some additional options. In VO and VEDA, we can pass arguments with an intent. We tried to convert this to Julia by automatically setting the intent in for immutable arguments and intent in out for immutable arguments. That means that arguments passed by reference go just in one direction, just into the direction of the device, if the object is immutable, and are also passed and returned when the object is mutable. So this is what we can do for passing an argument. The same way we can pass a mutable structure to a kernel. This is being passed on the call frame of the kernel, so it doesn't require additional transfers, and it can also be used to return results from kernel functions without additional reads to the memory. Calling vector engine libraries is possible for libraries which are loaded on the VE side. Here's an example for libc calls like getHostName or putString. Numeric libraries would need properly generated Julia interfaces. By the way, the VE side C-call is not the full Julia C-call. It won't load the shared object for you, so we have to use this peculiar calling convention. For numeric libraries, we could generate Julia interfaces. This is quite easy to do for CLibs, but is maybe a bit more difficult with Fortran. Here's a Fortran example. In order to load the library, we need to call something like this. VE module is loading the shared object into the vector engine's process space. And here we have a function that shall be called on the device side. Function compute _ dot being passed to vectors of float is calling the d dot _ function from the BLAS library. Device arrays are called VE array. They are created from host arrays. A_dev is assigned the VE array object. Once this assignment happened, the data is already allocated and transferred to the vector engine. We can retrieve results by creating a host array. The example shows the addition of two random matrices on the vector engine. So we define the function as add that adds every element of the matrix, which is linearized in this case. We allocate the matrices, random matrices A and B, and the result matrix. Then we create device arrays out of them, and finally we call the sadd kernel function on the vector engine and retrieve the C array as a result. Finally, vectorization. Vectorization is the most important thing for the vector engine. It has been built to run vectorized code. In LLVM-VE we use the Region Vectorizer, a modern outer loop vectorizer written by Simon Moll. It is a very good vectorizer, but it requires guidance. That means the loops need to be annotated in a particular way. We cannot use the loop vectorizer, the default vectorizer from LLVM-VE, because that one is producing a normal vector IR but not VP intrinsics, and that is not working with our backend currently. So LV is disabled in LLVM-VE. In order to annotate loops, we are using a new macro. The macro is called Vectorize. We also need to use the inbounds macro to remove boundary checking, as known from other approaches to vectorization in Julia. The Vectorize macro has some options. One of them is length equals 512. This tells the compiler that we are dealing with a single precision or integer 32 loop, and the compiler should try packed vectorization. Then there is the ifdeb option, which adds metadata marking that memory accesses are independent of each other. Of course, we'd like to have automatic vectorization. There is work ongoing on vPlan. vPlan is being converted, especially by the RISC-V developers, to produce VP intrinsics. By the way, RISC-V is also a long vector architecture, pretty similar to the vector engine from the instruction set architecture. There are other approaches in Julia to vectorization, other macros. So there's in base SIMD loop, there is a macro called SIMD. Unfortunately, this is not suited for RV. It annotates the loop in a different way and represents them in a way that is not understood by Region Vectorizer. And then I found loop vectorization.jl, which annotates loops with turbo. So there is no standard, in my opinion, for vectorization. Therefore, we just added another macro for this. On the right side, you see how to use this. And so we can use, we can vectorize the function vadd as opposed to the function sadd. Of course, in the first call to the function, we are paying the JIT penalty. So the call takes long, the second call takes short time for the vectorized code. And this is a scalar add without the vectorized annotation. This also takes long in the first call and takes longer than the vectorized version in the second call. Conclusion. I feel like a beginner to Julia, but I learned a lot in this exercise. I can say Julia is cool. It's easy to learn, but it's huge. It is simple to expand, and that hides a danger, the danger that it will be very difficult to establish standards. Julia on Vector Engine, well, it works. The basics work. From what can be done, it is probably pretty close to what GPUs can do. It can run kernels, it can use arrays. It should get support for the optimized libraries. Then we need guided vectorization in order to get performance. There is still a lot of work to do, and if somebody is interested to help out, please contact me or Valentin. Of course, we have to add the optimized libraries. It would be great to get a Vector Engine side Julia runtime. This is hard but not hopeless. We absolutely need to add multi-threading support for the Vector Engine such that we can use the cores, all the cores from just one Julia process. Then there is the task of data independence detection, which could lead to automated loop annotation with Vectorize or some other way of signaling the vectorizer that it's safe to vectorize loops. And finally, I'm dreaming of loop optimization control. There's a lot of potential in doing loop changes like merging, unrolling, interchanging loops. And with this, thank you for your attention.